Homework was to do some exercises from the end of the chapter and then set up Cloud 9. And I think I had posted on Slack just a few minutes right after class the quick fix for the assembly issue using ELF64 instead of...
ELF.
Huh?
Was it ELF64 instead of ELF or what?
Yeah, ELF64 instead of ELF. ELF is 32-bit. Let's talk about what ELF is. So it's I guess less awkward, and we don't just assume that we're talking about Mr. Gonzalez. If you don't get that, that's okay. If you do get that, my condolences. Okay. Right, so let's go here. All right, so last time, and we'll get back to Cloud 9 here in a few minutes. Last time we were using Cloud 9 to, we installed our NASM assembler, right? And then we wrote a file in there, so a text file that had some Intel-based x86 instructions. And then we assembled them. And then we attempted to link them using ELF instead of ELF64. And it turned out that Cloud 9 was actually a 64-bit installation of Linux instead of a standard 32-bit installation. And we kind of talked about that before when we kind of had this evolution of 32-bit to 64-bit processors. So now we're seeing more and more often there being a 64-bit installation of stuff. So Cloud 9 has a 64-bit installation of Linux. So in order to execute stuff on it, we need to create 64-bit executables. So then the question is what does ELF stand for? All right, so startup question to that would be, when I use NASM to take my input text file and convert it into something else, what is it doing? What is it actually doing when I give it we had our Hello World program written in assembly language, and then we're turning that into something else? What is that something else? Okay, a machine language of some sort, right? So it's taking our human-ish readable one-to-one language and converting it into something that's one-to-one on the actual CPU. Now, it ultimately needs to at what point do we actually run it is the issue here. So now it's in a format that knows how to speak right to the CPU. So if we think about this in real life, we talked about this probably way back in the 200 class, and we talk about high-level languages, low-level languages, and machine languages, and the human beings aren't going to do so well with the zeros and ones. That machine language thing really isn't a good fit for us. So now we have it in zeros and ones. It's converted our assembly language into a bunch of zeros and ones. What's next? When you have a program on a computer and you actually want to run that program, what happens? Who runs that program for you? The OS does. Okay? The operating system itself is the guy that's ultimately going to, when we double click on Microsoft Word, the OS behind the scenes is going to do the magic necessary to get Microsoft Word loaded into memory and ultimately delivered its processes to, well, processes need to be born and then delivered to the CPU and scheduled and a whole bunch of stuff that the operating system is doing for us behind the scenes, right? But now, before we can have it in that format, all we have right now is effectively a script. We're saying, here is the list of magic tricks in binary format to the CPU, as opposed to in x86 assembly format. Okay, here's my list of magic tricks. Now, we could take that right to the CPU if we had all the right plugins and stuff like that and say, go. But instead, what we need to do is we need to get it into a format that is actually executable by that particular operating system. Make sense? All right. So that's what the linking does. Okay, so when we do the link, we're looking for an executable and linkable format. Okay, that's what ELF is. All right, so it is a format that we know how to execute on Linux. All right, Windows, I'm trying to think what the name of it. Actually, Windows, if you use the emulator anyways, you could do ELF, but generally speaking, I haven't done assembly in Windows in 20 years, so I think anything I say right now might be made up. But ultimately, it's going to produce a .exe. That's not made up. that part's a true statement. All right, so this ELF is telling us what format do I need you to build this, or are we linking this for? Ultimately, so the operating system knows how to execute it and take over all the stuff so we can actually test it. Make sense? All right, so let's open up Cloud9 and see that work. C9.io. Let me elevate this a little bit since I know some of you. So there was the actual command. So we assemble it for ELF64. Then we do the linking. Here's our object code. That's the machine language code. And our output file is going to be a file called hello. And hello is the actual executable. So if we were thinking about this in Windows terms, this would be hello.exe. Typically on Unix systems, executables don't have anything special about them in terms of names. When I do ls-la, let's say, these commands right here tell us whether a file is executable or not. So here's hello. Notice it's been color coded in green, and it has an X for permissions. This is read, write, execute, read, write, execute, read, write, execute. This is for the owner. This is for the group, and this is for the world, everybody else. Okay, so everybody can execute this hello file here, but only the owner of it, us, can write it, can change the contents of it. So that's how it's differentiated at the in Linux, whether something is an executable versus not. It's in the permissions of it. All right, so then to run it, we'll do /hello. Now, what do I mean when I say /? And again, if I just do ls here, let's just do ls-a. So when I do ls, it gives me a directory listing. All right, and this directory listing shows me all the files that are in this directory. So I have hello.o, hello.asm, hello, readme.md, and then I have these three other things here. Let's talk about the .c9 first of all. So in a Linux system, does anybody know what it means when a directory name or a file name starts with a period?
System file hidden or something?
It's hidden. So as an example, I had to specifically do -a to show all there. If I just do ls, you'll see only the ones that didn't have dots at the beginning of them show up. Okay, so anything with a dot before it is by definition a hidden file. So if I do something like touch-lol or .lol, that creates the file. That's what touch does. It just creates a blank file that's nothing in there. Now I do ls, you'll see that guy doesn't show up. If I do ls-a, now you see it does show up. Make sense? All right, so I'll get rid of that file. All right, so this is a hidden directory for C9 that has some project stuff that makes their IDE work. All right, so this is kind of what marries those two things together. So you don't have to worry about that. That's a C9 specific or a Cloud9 specific thing. All right, so when we go back here though, every POSIX operating system, so from our perspective, every Unix or Linux operating system, and DOS has this as well. We'll have a dot directory and a dot directory. What's the difference between those? What are they for? You'll find it in 100% of directories. You never have to create them. It's part of the file system.
To go up one folder directory or to go all the way to the root? Or am I totally off?
No, you're not totally off. You're half off.
Cool.
Okay. Which one? Which? Oh, by the way, Alex was nominated for Student of the Month. He didn't win.
Yeah, I wanted to thank you for that.
Yeah, he lost.
I was gonna thank you with like money or something, but I didn't actually win. So
Yeah, no, I get it. CS people never win. Mostly because they're not deserving. Zach was also nominated. He didn't win either.
special call, bro.
Yeah, both are your losers. Just saying. Hey, hey, hey. All right, so yeah, I said you were half right, correct?
Yeah.
All right, so the dot directory goes up one level. So right now, if I do PWD, what does PWD stand for? I recognize that you may not know this, so we're trying to connect some of those. Present working directory. PWD is the current directory we're in, present working directory. So I'm currently in /home/Ubuntu/workspace. So if I do cd space .. where should that take me? Yep, up one level to the Ubuntu directory. So I'll do that. PWD takes me into Ubuntu. So it allows me to walk up one directory. So let me go back into workspace here. Once you get used to command line interface stuff, so I'll type CD and I'll do WOR, and then I'll just type tab. And as long as nothing else matches it, it'll finish it out for you. All right. So again, I'm in that directory. If I do CD space .. that's going to go up two directories. I'm going up a directory, and then I'm going into the .. directory of that directory. So that should take me into /home. Make sense? And if I do CD, actually, so is that what they say is, okay, yeah, so what they consider to be your home directory, if you just type CD and press enter, or you type CD space tilde, that takes you to what the operating system thinks is your home directory. In this case, they think your home directory is in /home/Ubuntu. So our workspace stuff actually lives in that folder. All right, makes sense? So that's what the dot's for. So what's the single dot? Your incorrect guess, was it takes you all the way to the root, right? So all the way to just /. So the / in a Unix operating system is equivalent to like the C drive on Windows. It's the very top level in the hierarchy of your file system. So what does dot do? If I do CD dot, where's that going to take me? Instead of CD .. So that's my present working directory. CD dot. Oh, it does something.
Hides or doesn't hide?
So the dot directory says this directory. You saw me do it a few minutes ago. I said ./hello. That says run the hello program in this directory. Make sense? So ./ says here, right here. Now, why, you might say, well, why? Why can't I just type in hello? Right? Now, depends. This starts going to, so I realize most of you haven't worked in Linux or Unix before, but you've worked in Windows. When I say environment variables to you, what does that mean? So let's come in here.
Available to you like so if you open a command prompt, the environment variables would be like, being able to run a Java command or a Python command or something like that.
That's a pretty important one. That's really the one I'm referencing here. There's a lot of different environment variables, but on Windows, DOS, you have an environment variable called path. Okay, so this is a variable that is available to your entire operating system. Okay, what's the path environment variable used for? What kind of stuff do we put in the path environment variable?
Things we want to be able to reference from anywhere. reference.
Okay, what do you mean reference from anywhere?
Be able to run or use from anywhere. You don't want to have to be in that directory, wherever that
Ah,
is.
okay, okay, yeah. So you're right. You're right. Um, so we put inside the path environment variable the path to all the directories across our entire operating system that we want our operating system to look in when we just type a command. All right. So for example, and some of you have had to mess with this before, like when you installed Java. If I type in javac and then press enter, what it's doing is it's looking at all the different places in the path environment variable where that program javac could be. And if it doesn't find it in any of those places, then it screams at you and says command not found. Make sense? So if I come out here, it would be interesting. Let's see if is javac even installed in this. I doubt it. No, it's not. So this says command not found, and that means that it's already checked in all of the places. Let me go back to here. We should have a bash rc, I think. Yep, so let's do more dot bash rc. Can we give you any path in here? Nope, you can only operate in your own directory. Okay, good enough. What was I talking about? Environment variable. So when I type in NASM like this, and I press enter, it has found that program. It's telling me I didn't give it enough command line arguments to work, but it found that program. If I type in which NASM, we know NASM's not in this current directory, right? So if I type ls here, I don't see NASM there, right? If we think it might be hidden, I type ls-a. It's not there either. Okay, but if I type in which NASM, okay, that's going to tell me where that guy actually lives. He lives in user bin NASM. So that is a globally available binary directory for anybody who's on the system, but we're on like a virtual system, so it's actually just for us. All right, but punchline is when I type in NASM right here, it found it even though it was not local in this directory. All right, so me typing in hello like that. Am I in the directory where it's at? Yep. So me typing in hello and pressing enter, and it says it can't find it. What does that tell you? What is not in our path variable? Not hello. We're looking for hello in a location. It would be the location of hello, right? So that directory, specifically, it's this directory. The dot directory. You can add to your path, always check in the current directory you're in. That's what dot is, the current directory. All right, that's not in there. So if I want to be able to run the hello program, I need to do ./hello. I'm giving it the full path to where that executable is because it's not finding it in my normal path. Make sense? Where is hello? It's right in this directory here. ./hello. It's full path to it. Make sense? And there's our running hello world program. All right, so, environment variables, these things, this is not a computer this is not a hardware discussion. This is the marrying between our hardware and our operating system. So if you kind of think about this course versus the 350 class, 350 being operating system really talks about the connection between the human being and the operating system and what jobs the operating system is doing at the level living above the hardware. What we're talking about in here is really the mesh between the hardware and the operating system on the other side, okay, behind the scenes. All right, so that path variable is something the operating system relies on, and it's where it looks for where your executables might be. All right, so what we've done out here is we assembled our file into object code. We then linked it into an executable. Okay. And then, so we linked it with the operating system's libraries. And that is what actually, remember when we looked at our code originally? Let's, do I have that guy in here? Where's my, oh, here, this guy. All right, so here is our assembly program we have up here. And remember the sys_write thing? So what is that guy? What kind of animal is sys_write? For us, it was a 4, number 4. And we said it referenced sys_write. Who owns sys_write? What is that guy? Yeah, it's a system call. This is one of the magic tricks that Linux knows how to do. Not Linux, not a CPU, Linux the operating system. All right, so we have a list of magic tricks that Linux knows how to do, and these are things that the Linux operating system, and likely most of them are going to be things that all operating systems know how to do. Okay, so we're going to be calling upon one of those magic tricks because the operating system already has a ability written into it for writing stuff out to the screen. Okay, we just need to call it the right way in order for Linux to work. When I assemble this program, what I'm doing is I'm changing. Remember, a low-level language has a one-to-one relationship with the CPU, right? So this line right here is equal to exactly 1 line on the CPU. So the move instruction is a CPU command. It's a magic trick our CPU knows how to do. And it has a destination and a source. So I'm moving this value into this destination. Assembling this program will take this line, as well as the other ones, and turn it into the binary equivalent. Instead of move, it'll be whatever instruction, whatever index the move magic trick is on the CPU. Instead of EAX, it'll be whatever index, binary index, the EAX register is referenced on the CPU. Okay? And then the number 4 will be a literal value, so it'll actually be the binary version of 4. Make sense? It's going to map that in binary, which is ultimately what the CPU is going to take as input. All right? It has not run yet. So we've converted this English-like assembly code into object code that would be understandable by the CPU. When we link it, that's when we give meaning to that 4. Okay? That's when we say, Linux, connect the dots and turn this into an executable that we can now run on this operating system. That make sense? Now, if we were running on another operating system where sys_write wasn't necessarily the number 4, so maybe we're on Windows or something, I don't remember if 4 represents the equivalent sys_write. It probably does for something this simple, but let's assume it doesn't. This would assemble. The assembler would assemble it. It's fine. EAX, as long as it's an Intel architecture, okay, an IA architecture, these things all exist. But when you actually went to link it, it's going to say, oh, wait a minute. I just tried to build an executable for you, and you're referencing something that doesn't exist. Kind of make sense? All right. So, in any case, we moved all these things around. We ultimately put them into the file. It then gives us a executable. We run it, and hello world prints out to the screen. Okay, now up here, EDX is the length that we're going to print. What if I just say 2 there, instead of the length of our string?
The length of the string is an integer, so we're going to take the first two.
HE?
An overflow error or something?
Well, so you suspect it might be HE. First 2 characters. All right, well, let's take a look. So I need to renaz them. All All right, I'm going to show you another shortcut command. I'm going to click on it. I'm going to type history, and if I just do history and press enter, you'll see it gives me a whole bunch of things like this. I'm actually going to do history, pipe to, grep, NASM. And this shows me all of the commands I've typed in that had the word NASM in it. So I'm taking the output of history, which is that big list of all the things I've ever typed on here. I'm taking that output, instead of to the screen, I'm piping the output into another command called grep. And grep does a lot of things, but we can think of it as like a filter. Okay, and I'm filtering on the word NASM. So this shows me just the guys that are related to NASM. Now I see that the command that I want to remember is this guy right here, right? And it's listed as command 24. So I can actually do bang 24. And that just did that line. Or I could have copied it and pasted it, same thing. But that executed that line. Okay, now we're all memorizing every one of these commands, right? Because there'll be a quiz. Just like programming, this is one of those things that after you've done it a zillion times, you'll remember it. Do it your way. If you want to just type in history and see all the things and scroll through those things until you find the one you liked and then highlight this guy right here and copy it and then paste it, that's fine. That's fine. Or if you want to give yourself a little cheat sheet that gives you the command you got to type in, it's fine. I'm just kind of showing you some of the capabilities of what you can do from the command line. All right, and then we also need to do the LD. So history, grep for LD. Here's this guy. So let's do bang 20. So now we have our output ./hello. Oh, did I not compile the right one? I did save this, right? So message length, I put in a 2. There's my message. There's my output. There's my file descriptor. Okay, that should be okay. Unless it's never actually using this. That'll be interesting. Could be the new syswrite doesn't actually use 64-bit syswrite, might not use the length, and might just figure it out. So we'll be able to.
Did you save?
I did. I just did multiple times, but yeah, I did the right command to save. Okay, there's that. There's that. Oh, this should actually just be hello. My NASM command was not lined up with the other command. My output, when I did that NASM command before last class, I did that. My output object file would be hello.o, which would then produce a hello.o, which then would allow me to do the link here. Hello.o output would be hello, which is the executable. So there's my hello, and there's my HE. Make sense? So a little getting used to doing some of these different things, but well, we'll talk about that here in a few minutes. Okay, so let me do this way. I want to introduce the registers. I guess technically, since we're dealing with 64-bit registers, let's do Intel architecture, 64. Let's just do registers. Should give us a nice Wikipedia thing showing us all of our registers, AX and BX and CX and stuff like that. No, I'll just introduce them. All right, so now we already talked about what registers are, right? Super fast, variable, built-in hardware. So we have several registers available to us. I'm going to treat it like we're dealing with a 32-bit operating system, so we have less registers to remember. So we have at the top level, and I'm not going to introduce all the registers right now, just kind of some important ones. So we have EAX, EBX, ECX, autocorrect, thank you, and EDX. Each of these are 32-bit registers. Okay, this is a 32-bit register. This is a 32-bit register. This is the 32-bit register. This is the 32-bit register. All right, so now let's just focus on EAX for a few minutes. Then we have AX. Okay, AX is the bottom 16 bits of EAX. So that's a 16-bit register. It's a sub-portion of EAX. And then we have AH and AL. That's A high, A low. This is an 8-bit register. This is an 8-bit register. Make sense? So what do I mean by bit? 32 bits or 16 bits or 8 bits or 8 bits. What do I mean by all that? Go ahead.
How much you can hold.
Okay, how much I can hold in terms of what?
Like in terms of like their maximum like value.
Okay, what values would go into a register? Because the registers, this is actually on the CPU, right? When I say, what is a bit?
Binary digit.
Binary digit, 0 or 1, right? So if I have something capable of holding 32 of those, I have 32 buckets. Looks like an array. 32 buckets, each one of those guys can hold a 0 or a 1. All right? The bottom 16 buckets actually have a secondary name. So I can look at the entire register, EAX. Draw a picture of this. Okay, so that's EAX. That. Let's say that's half. That's AX. And obviously it'll be a different color. Row. Oh, we're fine. AH. I will just assume that that was accurate. Good enough. AL. And then these guys should be a different color. All right, so the entire container, this is a 32-bit register, and in a 64-bit CPU, we'd even have a higher register where EAX was a lower portion of that. But dealing with 32-bit Intel architecture, which I'm pretty sure your book refers to, this is the name we give to the entire 32 bits. If we want to use only a portion of that, we can sub-reference the lower half of that through the name name AX. Okay. we can talk about the upper 8 bits of AX through AH and the lower 8 bits of AX through AL. Make sense? So 8-bit register, 8-bit register, 16-bit register, 32-bit register. Okay, and that's just for EAX. Now, we have several different registers. I was trying to give you the lowdown for that, but let's leave it. I was trying to give you a reference page. I'll find a good reference page for it. That might give us a pretty good one. Oh, here, assembly registers. This will give us a good list. Okay, so here's our 32-bit register, EAX, BX, CX, DX. You have AH, AL are the two parts of AX, BX, CX, and DX. Now, each of AX, BX, CX, DX kind of have a purpose. So when I say purpose, think back to when we first learned about loops. And we said that while loops lend themselves to certain kinds of problems, for loops lend themselves to certain kind of problems. Now, in terms of actual hardware, AX, BX, CX, DX, EAX, EBX, ECX, EDX, they're all identical. Okay? They are fast 32-bit or 16-bit or 8-bit hardware registers that are really, 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 really fast. Okay? They are all the exact same animal. And we're going to say that they're identical in speed. Technically, one of them is going to be a little closer or something to the CPU, so there might be some, fraction of a fraction of a fraction of a fraction of a nanosecond or something where one might be slightly faster. But in any case, but they each lend themselves to something. And what we really see by lending themselves to something is they are automatically used by some assembly language instructions to accomplish certain tasks. So for instance, when we look at the assembly language instruction for dealing with a loop, CX, which is the counter, is automatically checked. And we keep looping until CX makes its way down to 0. So we manipulate when a loop ends, because we kind of bounce between labels and stuff. We manipulate when it ends based on us changing the value inside of CX. Because that's specifically the place that the loop assembly language instruction looks at. Okay, pretty similarly to what we've kind of already talked about with our little Hello World program here, where we have seen that we've staged some values inside of some registers. And then we rely on those values being found by the appropriate system call when we interrupt the CPU and let the operating system pick up where it left off. Make sense? All right. Okay. Then we have some other registers, pointer registers, stack pointer, instruction pointer. So these are lower portions of 32-bit registers. We have larger versions of those. And then we have somewhere down here we're going to have flags. So overflow flag, direction flag, interrupt flag. Overflow flags used pretty often. Zero flags used pretty often. And carry flag is used pretty often. This guy. All right, we'll see examples of all of those. All right, so really what we're trying to kind of see here is the tools available to us. Because this can all feel pretty intimidating when you're first seeing it, right? Okay. Try to treat this stuff as if I'm showing you a new set of Legos. All right, and you unbox your Intel processor and you look at it and say, oh, well, here, I got 4 Legos right here. I have EAX, EBX, ECX, EDX. Like, oh, well, those are kind of big labels and then big Legos. And all of a sudden you realize, oh, this guy's got something in it. Okay, when you open up EAX, you realize there's actually a smaller Lego inside. That's AX. And then that guy opens up. It's like those Russian dolls, right? And that guy opens up like, oh, actually inside of AX is 2 even smaller Legos. AH, AL. All right. So now why do we need so many registers for holding different size values? And then even more modernly, with our 64-bit architectures, we're going to have 64-bit registers. And then a sub-portion of that 64-bit register would be a 32-bit register, which would then have two sub-portions of two 16-bit registers, which would then each have two sub-portions of 8-bit registers, which would actually be four 8-bit registers. Why do we need so many different size registers? And why are we kind of playing quadruple duty with these registers? Why have we decided we can use the entire 32 bits, or use half of it, or use half of each of those? Go ahead.
Is it because like each size register has like almost like a special purpose?
Okay. What?
Like some are better at doing certain things than others.
Okay. Well, so let's step back for just so I make sure that we're not going the wrong direction here. Every one of these registers are, in terms of hardware, identical. They're not wired differently. One's not better at doing something than another. That isn't to say that the language hasn't dictated that if you want to use, like I used CX as an example, that's our counting 16-bit register that the loop instruction specifically uses. So those two are kind of married to each other for that. If you wanted to build a loop that worked differently, that worked on a different register that you chose, you'd have to build a loop separately with jump commands, and we'll see how those work. Go ahead.
Would it be because they realize that some of the data that goes into the registers is smaller, and since there's so little there's so little registers that they want to make the best of what they have.
Yeah, we have to have flexibility, right? I mean, we don't have hundreds of registers to work with. Think about how complex some of the problems we solve in computing it, how complex those are. And I'm basically telling you that at any point in time, if we're thinking about the 32-bit world here, the most granular I can get, let's just keep it simple, just dealing with the four registers I've introduced, because you've kind of seen that there's some other ones, but there are 8 total 8-bit values that I can store at any point in time. Total. What's the biggest 8-bit number? 255? That's all ones in an 8-bit number. I can store 8 of those. 8. So do you suspect that if you can only remember 8 things at once in Call of Duty, that might be problematic? Game seems kind of complicated, right? That's all this guy can do. 8 of them. The reality is modern processors can do a little more than that, but punchline's the same. We are extremely limited on the number of things that we can store simultaneously in a CPU. So we're going to be very reliant on being very organized with where we store stuff, when we use stuff, how we utilize this thing called the stack to temporarily unstore things and then restore things. So maybe we use our registers for one problem and we say, okay, I'm going to come back to this in a few minutes. So I want to copy all the values from those onto the stack so that I can now mess these up. I can do something else here and in a few minutes come back and restore them from the stack. Make sense? You're kind of playing this game with very few resources. So we're limited. We have to become problem solvers with a lot of constraints. Now, when you think about it from a Java perspective, a high-level language perspective, what are our constraints in that? What constrains us when we're a high-level language developer? We're not constrained by much, but there are constraints. What are they?
Variables we can use.
Okay. So how are you mean the number of variables?
Like the types of variables.
Okay. So the variable types. Yeah, that's a constraint. We have a lot of flexibility, but we have to play within the rules of Java. Fair enough. What else? I've already said it. Maybe number of variables. So we have 8 gigs of RAM to work with. So yeah, slightly limited. We can only hold like 4 billion integers. So as long as we don't write a computer program that we need to remember more than 4 billion things at the same time, we'll probably be okay. So we're constrained there. What else are we constrained on? Is it fair to say that we're not constrained very much with a high-level language? We're constrained more than, human beings just kind of happy-go-lucky. I just want to do whatever I want to do. And then all of a sudden you get down to programming, it's like, oh, well, I feel like this is so difficult because Java is always screaming at me that I tried to do this and it doesn't want me to do that and all this other stuff. This is going to be worse, right? We're in a maze and we only have 8 doors. And they might all be locked right now. Now we got to figure out how do we get out of those. How do I preserve data so I don't destroy what's in AX right now? But at the end of the day, I need to use AX. Okay? My next instruction is going to go in there. Where do I put that guy? So this is all dealing with how computer architecture works. What are our little magic tricks? What little tools, what Legos did we invent to allow us to manipulate this relatively small number of resources in such a way that we can solve large, complex, generalistic computing problems? Make some sense? All right, so let's look at your book here. And let's go to instructions. Okay. Now I wish... Oh, your book's actually talking about a MIPS instruction set. That's fine. It's not a big deal. Let me look at something here. Back 86. Oh. Actually, there might be a web one. That'll actually be ideal. Nope, that's a Windows one. Okay, I think this will do what I needed to do. Let me try this. Let's go back into our code here. I'm just going to steal our code. I'm going to paste it in here. After what?
I'm guessing it's after start.
It doesn't like this format. Is this is x86? There. We'll let it load its example and see what that guy looks like. Oh, it looks like it just wants you to start with your instructions. Okay. The reason I want to look at this is it shows you the individual steps of the... I wonder if that's going to use that. It's gonna... Okay. Oh, this is kernel stuff, so that's not going to do us any good right now. I just want to be able to look at stuff. Okay. What are you complaining about? No, I'll experiment with this and figure out one that'll let us do what I need to do rather than taking up class time. But ultimately, what we want to do right now, the way we can test our program, if we think about this in terms of Hello World or like a Java program, is we would write something and then we would output a result to the screen, right? That's how we test it. Well, now we're dealing with things at a very granular level. So it's going to be helpful for us to be able to step through our assembly language code one line at a time and see how the registers are changing. All right, so there's these programs called emulators, 8086 emulators. And what it does is it emulates a 32-bit Intel architecture. And it shows you the list of the list of the flags, the list of the registers, the list of all that stuff. And ultimately, you can step through your program one line at a time and see those things change on a line by line by line basis. Make sense? So kind of the punchline with that. So I'll find a good one. There's a really good one for the PC that I'll link up on Slack later today. All right, so let's go back here. So kind of as you walk through here and you see some of the different things you can do, we start off with our basic add instructions. So, and this is talking about a MIPS language. So one thing to keep in mind is we have two things that we're looking at in here. One is our assembly language tutorial, which is an 8086 thing. Your book uses examples from an instruction set called MIPS, which is not Intel, but you're going to see there's lots of similarities. It's not going to like break anything, but just something to keep in mind as you're going through there. So let me do this. Assembly language tutorial. Let's bring up the one we've been using. This guy right here. And we have read our introduction, and then have you done the environment in here? I think that's kind of what we set up last time, right? We got our environment set up. So if we go to basic syntax, let's just start there. This is 8086 version of add, as opposed to what your book says where there's three things. And this gives us an interesting dichotomy to look at. So if we look at the add instruction in MIPS, older processor type. This is the destination. The destination will always be on the far left. These are the two operands. So we're taking B, which is, think about this like BX. BX, CX, adding them together, storing the result inside of AX. All right, so the answer of these two numbers added together will be stored inside of this guy. Now, our assembly language, so this is MIPS assembly language as opposed to Intel architecture-based assembly language. Who are those languages written for? Who's the audience for an assembly language? Just like who's the audience for the Java programming language? Us, people, right? So we are the target audience for an assembly language. Even though it seems tedious and why would anybody do this to us, we are the target audience. Now, how many of you find it most convenient to count in binary or octal or hexadecimal? I just can't do decimal anymore. It's not convenient for us, right? We can work with it, but it's like an exercise. It's convenient for us to think about things in terms of decimal. So one thing you'll find with, I don't want to necessarily promise all assembly languages, but most assembly languages, certainly are Intel-based ones, is the default type that you can put into registers will be decimal. It will convert it into binary for you. I promise you. If it's a 32-bit register and you put a 5 in there, it's going to give you the 32-bit version of the number 5. All right, it's not going to store a 5. It's going to store a bunch of zeros and ones. All right, but you are allowed to use the 5. When you go to print it out, it will show you the 5. Okay, not the zeros and ones, unless you make it show you the zeros and ones. That make sense? Okay, so Let's go into the tutorial thing here. So it's using 32-bit registers here for the add instructions stuff. So here are some instructions that are available to us. So we have the ability to increment the memory at a particular variable, in this case count. So we really have 3 different things that we could be working with. Well, I guess, well, yeah, 3 different things. If I am saying, let's use move as an example, okay, to get our 3 things. So when we have our move instruction, it's move dest source. That's the syntax for this guy. Where dest can be a register or a variable. Source, what do you suppose source can be? I'm moving this value, whatever source is, into this destination. What are the options for source? Say this again.
Variable type.
So a variable, okay. What else? There's 3 of them. We're short. We're short 2. All right. Yeah. Somebody else. Go ahead. Register. Okay, like it. All right. So our source can be a variable, can be a register. What else? This last guy is often overlooked. It's also the most common. Go ahead. No. I mean, I'm going to say no, technically. I mean, the answer is no. It's the wrong answer. Huh? We're closer there. A literal. Okay, a literal value. Okay, so in our world, most literal values are going to be integers. In fact, in assembly language, it's always going to be a number. Because if we're referencing a character, we're going to give it the Unicode version of that character. Okay, so a literal value. So like 5, I can do move AX comma 5. So I can do something like this. Move AX comma 5. That will move the literal value 5 into the register AX. Make sense? All right, so we kind of have 3 different values that we can work with here. 3 different Legos, if you will. All right. So here's an increment command, a move command, an add command. Then we have and commands. Tell me about and. When do we use and in Java? Okay, Boolean expressions. What's a Boolean expression? Any expression that boils down to a single value of true or false. So we use and to say, is it cold outside and is it sunny? Stuff like that, right? Now, the idea of a Boolean expression exists in assembly language, but just like everything else, it exists at a bitwise level. So when we're talking about ands and ors in assembly language, we're talking about anding 2 numbers together, doing a bitwise and or a bitwise or. All right, so like as an example, so and we have dest and source. Dest can be can it be a variable? I think it can be a variable. And a register. Source can be a literal, a variable, or a register. And how does this guy work? We might do something like and AX. Well, here, let's look at a legitimate example. So let's do move into AX the value 110. Let's actually work with 8-bit registers, so I don't have to put as many zeros and ones. 110 11001. So there's 8 bits that we moved into AH. What's AH? What register is AH? How many bits is in AH? 8-bit. It's an 8-bit register. It's it's the left side of AX, the left half of AX. All right. So I'll move into AH 1101101. And then what I'll do is I'll go ahead and I'll do and AH, comma, 10101010. Something like that. Now remember, the syntax for this is the left-hand side is the destination. So the result will end up in AH. Okay? So when I add these two numbers together, anytime I see a 1, where I see two 1s, it'll be a 1. Whenever I see only one 1 or no 1s, it'll be a 0. So 1 and 1 is 1, 1 and 0 is 0, 0 and 1 is 0, 0 and 0 is 0. Okay? So when all is said and done here, AH will hold the value of 1, 0, 0, 0, 1, 0, 0, 0, which is those two values ANDed together. 1 and 1 is 1, 1 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1, 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0. Make sense? Now at this point we have no idea why we might ever want to do that. Well, it's a Lego. Okay. We have a tool. And we're going to see reasons to do this stuff. All right? Let's look at another example. Let's do, we'll just keep the same value we have in there. And we're going to say, or, I'll steal that guy, AH, comma, that. All right, and forget that we ANDed it, so we'll just do this as a fresh example. In fact, let's just dump it. All right, so we moved into AH, this 8-bit number, and then we're going to OR it with this 8-bit number, storing the result back in AH. Now, OR says one or the other or both. So when all is said and done here, AH will hold the value of 1, 1, 1. Let me line these guys up a little bit better for my own sanity. So 1, 1, 1, 1, 1, 0, 1, 1. That. 1 or 1 is 1, 1 or 0 is 1, 0 or 1 is 1, 1 or 0 is 1, 1 or 1 is 1, 0 or 0 is 0, 0 or 1 is 1, 1 or 0 is 1. Okay, another Lego. So these are bitwise ANDs, bitwise ORs. All right. Another guy is called exclusive OR. Okay. Exclusive OR says one or the other, but not both. So exclusive OR is only a 1 when there's exactly one 1 between the two bits. So this would be 1 exclusive OR 1 is a 0. 1 XOR 0 is 1. 0 XOR 1 is 1. 1 XOR 0 is 1. 1 XOR 1 is 0. 0 XOR 0 is 0. 0 XOR 1 is 1. 1 XOR 1, or 1 XOR 0 is 1. Make sense? So bitwise XOR, or XOR. All right, so more tools. And the reason why I want to be able to show you the emulator thing is so that you can actually see as we step from line to line to line, you'll see the registers update with these zeros and ones and that kind of stuff. Okay, so we can perform some Boolean operations on our registers. So you get values loaded into the register. From our perspective right now, the values are loaded into the register for some reason. Most of this right now, we opened up the box of Legos. We're just seeing what's available to us. We're not actually building anything. We don't know we're going to build a castle or a car or whatever. We just have Legos. It's like, okay, you can do a XOR. Cool. Sort of, right? Okay, whatever. So we know about some of our registers. We know how to move stuff into our registers. We know how to AND, or XOR with our registers. Okay. Let's go back here. I'm not going to talk about this mask thing yet because that's a lot of times what we're using these things for. We can increment the value of a register or the value of a variable, and that will add a decimal 1 to it. Now, before I forget, just so I'm not giving you bad examples here, in order for this to work, since I mentioned a few minutes ago that human beings, these languages are targeted at human beings, right? And we like decimal numbers. So this value right here would actually be treated as a decimal value by the assembler, when clearly it's not what we meant to do, right? We wanted these to be binary values because we were doing this bitwise thing. So you would put a B at the end of them. This is our output, so don't worry about that. But this B tells us, well, tells the assembler that this number is in binary format now. Similarly, hex would be an H for hexadecimal number. All right, that makes sense? All right, so we saw hello world, we saw compiling and linking. Okay, here's our example that we've already kind of talked about here. Forget about the pointer registers and those guys for right now. We'll come back to them. We just want to have kind of an appreciation that we have a whole bunch of registers to work with. Okay, so now here are some system calls available to us in Linux. We've already met syswrite, which is system call 4. Sysread is system call 3. Sysfork is system call 2. Sysexit is system call 1. And then sysopen, sysclose, these are for file I/O stuff, is in 5 and 6. Okay, and there's more than that, but those are some sample ones. And this tells us what parameters are expected. That make sense? So, in this case, just going by this chart, the most number of parameters that we can give any system call is 5. Right? That means that every system call that an operating system produces, put yourself in the shoes of an operating system writer. Every system call that you write has to be written in terms of that number of system calls, or that number of registers. You can't take 8 parameters in. We don't have room for 8 parameters. So you got to figure out other ways of doing things. So you can fake it. You can maybe say, well, I'm going to write this super special system call where I'm going to require the extra 9 parameters to be put onto the stack in a very certain order. Don't worry about what the stack is right now, but you can play with things like that. But this kind of goes back to this idea that we're playing this game, this balancing game between doing complex things. And every single time a new processor architecture comes out or a new version of an operating system comes out, how do we play the game at a higher level while still working with this limited number of resources? That makes some sense? All right. So just want to kind of see where we're going next with this guy. That's probably... Okay, so let's pause that there. That's as far as I want to go with that. So in your reading, you have gone through chapter 1, and our homework for today was to do some exercises, right? Okay. So for next class, let's do... Let's do 2.1 through 2.6 in the book. And let's leave it at that. So do all the exercises for 2.1 through 2.6.
Read it.
Read it and do the little, do the stuff in there. Let me update our thing here through 2.6. All right. All right, so go through 2.6. I'll get your assignments graded before Thursday, and then we'll probably have a small assembly assignment over the weekend, but I want to make sure I can give you 2 good sources for 8086 emulators for Windows or Mac people. All right, I will see everybody on Thursday.